So a power series is an infinite polynomial where the terms that are being raised, a polynomial is just a bunch of variables that's being raised, or one variable being raised to power, and then the next power, the next power. So power series is essentially a series, an infinite polynomial where your variable or your variable minus a constant is being raised to a power and then added to another one. So it's essentially an infinite linear combinations of x minus a to some integer power n, where n goes from 0, anything with 0 power is 1, so that's just a constant, all the way up to infinity. So we have had Taylor polynomials, or some of you might also know Maclaurin series, which is really just Taylor polynomials, where a is equal to 0. And in those cases where a is equal to 0, it makes life a lot easier because you don't have to carry that a around. So that's a power series. Any function that we know of can be written as a power series, and some of them need special cases where it can be written as a power series for some smaller interval, and not necessarily all of them. So if you look at examples like the ln function where it's undefined at 0, then the power series obviously cannot be defined at 0. So we have to take a look at when the power series converges and the interval in which it converges. So some old definitions here of power series. Power series is convergent at specific values of x if its sequence of partial sums converges. Now that definition is a little bit more technical than what we need. And in fact, we probably won't be relying on this as a definition for us to show that something converges. If it doesn't converge, then it diverges. Every power series has an interval of convergence, a set of x values where they converge. In fact, the interval convergence set of real numbers where there's actually a center of the interval convergence, and then it converges to the left and to the right of that center, and it goes as far out as it needs to go before it doesn't converge anymore. And so that distance from the center to the edge of where it converges is called the radius of convergence. Radius of convergence of power series is some positive value measurement from the middle to the edge of where it converges. Because your infinite series is going to converge within that radius, and outside of that radius, you're guaranteed that your power series is going to diverge. So power series, think of a power series as a polynomial. And polynomials are nice to deal with. They're continuous, differentiable, and they're got all kinds of special properties. And so if you're trying to mimic something that's not continuous with a polynomial, then at some point that thing that's not continuous is going to break. But your polynomial has to stay together. So it's going to break where it's going to break. But what's going to happen is that it's going to break on one side, and it's also going to break on the other side. What? Did you say thanks? I was going to say whatever that means. Oh, so I guess we should have talked about that first, huh? So some of the power series or some of the differential equations that we'll deal with, uh, we don't have any good ways of solving for them. So we've only learned like a handful of um, techniques, especially for the higher order differential equations. We've learned the homogeneous with constant coefficients. So that's a big restriction already, is that your coefficients have to be constant. We took a look at some examples of non-constant coefficients in Cauchy-Euler differential equations, but those are special too because they have to match the power. The power of x has to match the derivative. So that's a special case. Now we want to see if we can go to a more general case to be able to solve for more general differential equations. And we don't have techniques for them. And so what we're going to do is we're going to use power series to represent the function that we're solving for as an infinite series, because your infinite series, we're taking derivatives and integrals of them. We can take derivatives of integrals and integrals of these power series anytime we want because they're just polynomials. So what we're going to do is we're going to use power series to solve for them. Now the hard part is that we're not going to get a nice function. Maybe we are, if we actually can get a nice function, but chances are your power series is not going to be something that's going to be nice that we can say, oh, that's just equal to cosine, or that's just equal to e to the x or something. So that's why it's more general. So think about it like I don't know if your Calc 2 gave you this problem, but like the integral of e to the x squared, there's no e to the x squared. There's no integral for that, right? You can't just do a u substitution because there's no other x to cancel with. And so what people tend to do is they use Taylor series or power series to extend it, and then they just get approximations. So anytime you stop with a power series, it's going to be an approximation. And to get the exact value, you have to go off to infinity. And so based on these power series, you end up with new formulas or new functions that cannot be represented by the formulas that we use from pre-calculus, for example. So, but they are still valid formulas, and some of them are so common that they give names for them, and they only define them through an infinite power series. All right. So back to old definitions. Old definitions. So interval of convergence. The radius of convergence is where this thing converges, and the interval of convergence is going to be basically everything within the radius of convergence. And then the endpoints, we're not sure what's going to happen to those endpoints, and so we have to test the endpoint to see if they would actually converge. Within the interval of convergence, power series converges absolutely, which means if you take the absolute value of it, it will converge. The other thing that's not defined here that might be something that you might remember is that if the absolute value doesn't converge, but if the alternating series ends up converging, then it's called conditionally convergent. Also in Calc 2, we learned a lot of different tests to determine if a particular series converges or diverges. Integral test, comparison test. But for us, we're going to stick with what's called the ratio test. And the ratio test is basically taking the ratio of two consecutive elements in the series. So the n plus first term divided by the nth term of the series. And then that ratio kind of tells you what's happening to the series. And so you take the limit as n goes off to infinity, and there's three possibilities. If that limit is equal to or is less than 1, then we know it's going to converge absolutely. If it's bigger than 1, then we know it's going to diverge. And if it's equal to 1, we don't have a specific conclusion for that. Okay? So maybe we should take a look at some examples of power series. You guys tripping? So should we, let's do e to the x? No, let's do one of the trig functions, sine x. Cosine x? Let's go from minus 6 to 6. All right, so we know what the cosine function looks like, right? Of course we do. And so a power series, power ranger or power range, power. What goes in here? I would say A and N. 1, that didn't work. I need help. Oh, it's not power. It's called series. Three elements. This really only helps if I know what I'm doing. Oh, we have to be in parentheses. Series. X naught, and N. All right, here we go. So I can go all the way up. So since I have a computer like this, I can go as far as I want to, like up to 20th degree. And so I have 1 minus x squared plus. Do you know what these numbers in the denominator are? So 2 factorial, 4 factorial, 6 factorial, 8 factorial. These are just factorials. And if you remember the cosine function, it's an alternating series. The cosine is an even function, right? And so all the powers are even. And then it's really just x to the 2n divided by 2n factorial. And then here they give you some extra stuff to say that if you want this to actually be equal to f of x, then you need to consider other terms that are higher power. So what's interesting about this is that if we, let's see, I think you do normal to get rid of that O term. So you can graph these things. What did we go from, -6 to 6? So if you can see, they look pretty much alike, right? This looks just like the cosine function that we saw earlier. Well, they look exactly the same. What is the difference? Let's make this go larger, from -16 to 16. Let's make this go from -16 to 16. What? So it looks a lot different now, right? I guess it'd be better if we can see them together. Let's see if we can put it together. What? What? Are you guys sleepy? I think we need to change a color in one of them. Let's change a color for this one. Uh-oh, now what happened? Oh, there we go, now it's red. So this is what happens. If you look at this graph, right around 10, between 10 and 15, it kind of shoots up. That's because the polynomial wants to go off to positive or negative infinity at some point, right? But we're trying to mimic a periodic function that goes between -1 and 1. So at some point, it's going to have to take off. So let's put all these commands together. So you got f of x, you got the series for f of x, and then let's show this. Okay. So if we change the n to, for 20, 40, let's go 30. So it spreads out a little bit more, right? You got 30 factorial down here. Look at that. It's a big number. All right, so now let's see if we can put it all together. See if this works. Uh-oh, doesn't work already. Not responding.
Oh no, too big. Oh no,
I'm bored.
I got.
I'm boarded. All right, so that didn't work. Let's move on. Oh, what happened to my notes? So let's take a look at the ratio test and how the ratio test is used. I don't know if we'll use much of the ratio test, but it's implied in a lot of the stuff that we'll do. So let's just get some good practice on what the ratio test does. We want to find an interval and the radius of convergence for the following series. Uh, this is an infinite series. A is equal to 0, so it's centered around 0. So already I know that at 0, it's going to converge for sure, because when x is equal to 0, then you're just adding up zeros, and that's going to be equal to 0. So the question is, how far is it going to converge? And however far it's going to converge to the left is going to go the same distance to the right. So let's do the ratio test. According to the ratio test, we're going to take the n plus first term, x to the n plus 1, divided by n plus 1 quantity squared. That's the term that we're going to put on the numerator, and then we'll take the nth term in the denominator, and then we want to take the limit as n approaches infinity of this thing, technically with the absolute value. So if you do the reciprocal, and a bunch of things are going to cancel, or not a bunch, but at least x to the n plus 1 and x to the n. So there's n x's in the denominator, and there's one more than that in the numerator. So that these things will cancel. And then the other one you can't cancel, but we can combine it into one power. So limit as n approaches infinity of n over n plus 1 squared times x. And since n are always positive numbers, we can just take them out of the absolute value sign. In fact, this x over here is by itself not related to n, so we can take that outside of the limit, or we could just consider this limit without the x, absolute value of x. And if you take this limit as n goes off to infinity, you get n squared over n plus 1 squared, and you could use whatever you want to use, divide by n squared or L'Hopital's rule or whatever, but your answer is going to be 1. Okay. So the limit of this thing is equal to 1 times x. And so according to the ratio test, if the limit L, which is absolute value of x, is less than 1, then this is going to converge absolutely. And if this is bigger than 1, then it's going to diverge. And if it's equal to 1, that means if x is equal to plus or minus 1, then we don't know what's happening. So by looking at this, it looks like the radius of convergence is just going to be 1. So we know that between -1 and +1 is going to converge. And we know that beyond that, it's going to diverge. What we don't know is what's happening exactly at those points. And if you're looking for the interval of convergence, then we want to know what's happening at those points. Yeah, so we're going to plug it back into the series. So when x is equal to -1, let's do +1 first. Let's do +1 because the -1 will make it alternate. So if you do the absolute value, if you do the positive ones first, then you're going to check if it's absolutely convergent. And if it does converge, then for sure the other guy is going to converge. Okay? If you check the -1 first and it converges, then you're forced to check the other one, the positive one. Yeah, so let's check the positive one. So we're looking at the series 1 over n squared. So do you know what this is equal to? I don't know what it's equal to. But do you know if it converges or diverges? This converges. Why? I don't know. Go back to Calc 2 and figure it out. You can either use the integral test, integrate 1 over x squared from 1 to infinity and see what happens. Or you can remember that this is a p series. Ooh, remember that? Done. Are you p serious? Okay, so if this converges, then that means it absolutely converges because it's positive. So without even checking, since 1 over n squared converges, -1 to the n over n squared also converges. Then the -1's going to converge automatically. If it diverges, then you have to check. So if the positive one diverged, then you would have to check the alternating series to see if it still converges. But this is why you do the positive one first. If the positive one converges, then you're done. So we can conclude that the positive and negative one's also included. Yes. Well, the P series. Do you guys know what the P series is? I'll look it up. We can. I really want to get this to work now. Let's see if it'll work for me. Oh, yeah, that's right. Normal. It's not responding again. No, I've had these animations already. Plot, f of x, series, plot. Let's call this something. Um, oh, I think it works. Oh, it doesn't work anymore. All right, we'll come back to it later. So, how is this applied to whatever it is we're doing? Oh, here's some new definitions and some important series to remember. Uh-oh. All right, let's start with the definition. A function is said to be analytic, so this is new. This is something that we didn't see in Calc 2. Function's analytic if it can be represented as a power series um, in x equals a. So analytic just essentially means it's differentiable. And then a couple of series that we should already know. We used e to the x, cosine x, and sine x to kind of prove Euler's formula. E to the x, e to the ix is equal to cosine x plus I sine x, something like that. So the left side is has the e to the x, the cosine, and the sine. The right side, this first one is sometimes called a geometric series. And then here are a couple of other results that come from the geometric series. And notice the radius of convergence for the functions on the left side. They're infinitely the radius of convergence is infinity. It goes from 0 to positive infinity, 0 to negative infinity, and it's going to converge for all real numbers. Whereas these functions on the right-hand side have a radius of convergence of 1. And then if you check the endpoints, you'll see that some of them converge at the endpoints and some of them don't. And this one in the middle converges in one of the endpoints, but not the other one. So checking the endpoints for the radius of convergence is important. It's called radius of convergence, by the way, because when you think of radius, you think of a circle. This thing applies to complex numbers. And complex numbers can be expressed as numbers on an xy plane. And so when you pick a particular point on the plane, you could take a look at a circle around that point and saying that a bunch of numbers or the functions are going to converge for everything within that circle and diverge everywhere else. So that's why they call it a radius convergence. All right. So here are some important series. There's some algebra of series that we should know. We should be able to add, subtract, multiply, and probably not divide. And compositions of series are also important things to be able to do. In my notes, I have a handful of examples. And I even threw in the example with the Euler's formula. So you can compose a couple of functions if you know the functions. If you know e to the x, then you can find out what e to the negative x is by putting negative x in for x. If you know x squared, e to the x, if you know e to the x, you can figure out what e to the x squared is by putting in x squared wherever you see e to the x or wherever you see x. And here's just an example of Euler's function, a way to prove Euler's function, which we already did. Okay, but there are other things that you should probably know, and that's let's throw in a couple of other examples here. So x times e to the x, right? So if you know the series for e to the x, then you can just distribute. Technically, you're taking this x and you're distributing it to that infinite polynomial, but you can easily write that as just n goes from 0 to infinity of x to the n plus 1 over n factorial, right? So this one, kind of like the same thing. Well, kind of like, but not really. Uh-oh, what happened? So it's going to be x squared e to the x minus e to the x. So that's x squared x to the n over n factorial minus x to the n over n factorial. So this will end up being what? X to the n plus 2 over n factorial. Okay? Why don't you guys spend about 3 minutes trying to figure out how to combine these two? Think about it. Write that on a piece of paper or something. No. Okay. So the thing to look for is you have to try to ask yourself, can you find a pattern here eventually? And so 1 over 4 factorial x to the fourth. What if I say dot 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 and I want to go to the nth term? N or n plus 1? Okay, you see that pattern? Okay, so except for this first one that probably didn't work with us, or maybe it did. No. So except for the first two terms that didn't work with us, we just kind of have to leave that aside. Yeah. Oh, yeah. So this should have been. So what should this be? Yeah. Okay. So this is one way to express this. Let's try to see if we can take a look at another way to express this. Do you guys know how to shift indices? Indexes? So, like in this case, instead of starting at 0, what if instead of starting at 0, I want this series to start with 2? If I want this series to start with 2, but I want to have the same results over here, what do I need to do? Add 1 to the n? Just 1? So my first one should be 2, right? N is equal to 2. So my first one is n is equal to 2. So this would just be n. And then this would be, I want this to be 0 factorial or 1 factorial, but so I can write it like this, shifting the indices. Right? Is that is that making sense? No? Say it again? Oh no, I went back to the original problem here. So I said if I'm looking at this series and I want that to start with 2 instead of starting at 0, then if I were to write this out when n is equal to 2 to begin with, this is going to be x squared over 0 factorial plus x cubed over 1 factorial plus x to the fourth over 2 factorial. And you'll see that this looks just like the series that we were looking at earlier, this one. So what I'm saying is that this series here is the same as this series here. Okay? So I think if those two are the same series, then this original problem that we had should equal to that, and then minus, right? Wait, did we accomplish anything here? Not much. So what do we accomplish? Well, this thing, let me rewrite this over again. And then for the second one, I have the matching x to the n powers that I can combine them with. But then I start with 2 here and I start with 0 here. So let's get rid of the 2 of them. So you see what I did here? I took out n is equal to 0. And n is equal to 1, so that now I'm starting with n is equal to 2. So now I think from here I can be ready to combine this series with this series, and then we just have an extra couple of elements that are sticking around outside. And then now I have a series that starts with 2 to infinity of 1 over n minus 2 factorial minus 1 over n factorial. And each of them has a factor of x to the n, so I can just factor out an x to the n. Okay? This is what you're going to have to do a lot. And this will, in differential equations, this will take out a page that's going to be about half of your problem. And then the other half would be trying to find patterns. Okay? Unless you write small. Yeah. Yeah. Write out the terms, shift the indices so that they align, combine them, and then try to figure out what your y is. All right? So let's try to do one. We actually know the solution to this. This is a first order differential equation, and we can find a solution to almost any first order differential equation. Do you know the solution to this? Just by looking at it? Imagine y prime equals negative 1 times y. Now do you get it? E to the negative x. So it's c times e to the negative x is your solution here. Okay, just keep that in the back of your heads. But let's see how we can use series to see if we could solve for this. Okay, what we're going to assume is that the solution looks like a series. And so a general series, you know that 1 over n factorial that we have, that's like a constant that you can just pretend it's sitting next to the x. And so that's a c. And then there's a whole bunch of them. Each of them might have a different constant. So there's a c sub 0, c sub 1, c sub 2, c sub 3, etc. So we want to figure out what c sub n is equal to for us to find the solution. So we have y here, but we need y prime. And this is the beauty about series, is that you can take the derivative of these polynomials. So y prime, imagine an infinite polynomial, and you're taking the derivative one by one. So a derivative of c sub 0 is a constant that's just 0. A derivative, maybe we should write it out a little bit. Y is equal to c sub n x to the n. I'm rewriting it. N goes from 0 to infinity. But now over here, I'm going to write c sub 0, constant, c sub 1, x plus c sub 2, x squared, plus c sub 3, x to the third, etc. Okay, so that's your series. Now imagine taking the derivative of this. So the derivative of c sub 0 is just 0, and then c1 plus, and then the 2, c2, x to the first power, 3, c3, x to the second power. So can you tell me what the general term is? If I were to tell you what's next after this. So it'll be n goes down. I mean, you can see it here, right? N goes down, c sub n, and then x to the n minus 1. Now, is this right? This isn't quite correct. What's wrong with this? Why isn't this quite correct? Not that it's not correct. We can clean it up a little bit. No, not necessarily. You can what? Look at my starting point. Yeah. It's 0, right? But when n is equal to 0, what happens? It's this term right here. We don't need that. So why don't we start with n is equal to 1? So let's put this series into your differential equation. So your differential equation then is going to look like a series going from n starts with 1 to infinity of n c sub n x to the n minus 1 plus the series, that's just y, n goes from 0 to infinity c sub n x to the n. Well, if I say n is equal to 1, I might lose c sub 0, so I want to make sure I keep the indices properly defined here. The first one, the second one, I can get rid of it because that's just, it's 0. So we can get rid of that. So now, this is the same problem that we had, well, a little bit different. You know, the 3 minutes where I asked you to figure out how to combine these? Let's try to combine these. So the way I want to combine them is I want them to have the same power. And so what I want to do is I want to shift the index on one or the other so that they have the same power. So shifting the index, I think if we start here, Do we want to go to 2? I don't know. So I want this to be n. That's like my dream, to get that to be n. Well, you know. So here's the trick. If you add 1 to all the n's inside of your summation, then you're going to subtract 1 from your index. Okay? I usually rewrite it with a different what do I want to say? I want this to be k. So I don't know if I want to put this one here. I want this to be k, and so whenever I add 1 inside of my series, I'm going to subtract 1 from the index. So I would have k. So in here, I'm going to add 1. And then here, I'm going to subtract 1. So I start with 0. For this one, I'm going to keep it the same, but since I'm using k, I'm going to switch to k here also. So no shift in k here. And let's see what happened again. We add 1. We add 1 in here so that everything is just a k, and then we subtract 1 from the power, or from the index. So now I have the same index and same power, so I can combine them, right? K goes from 0 to infinity. Now I'll combine them. And I'll factor out an x to the k. So this thing factored out an x to the k. And then this thing factored out an x to the k. Okay? So this is the step right here. These 3 lines are going to be the hardest part of the problem. Yeah, but I did that over here. I did my shift over here. But for this one, I'm not going to change the shift. I'm just going to change the variable. Since it's a dummy variable, and when I'm looking at it line by line, I kind of want to have the variables, the indices, to be the same. So this changed to k, and I could have left this as an n, but if we leave it as a k, it might be a little bit cleaner. All right, yeah. Up here or up this one? Oh, because for every n in here, I'm going to replace it with n. I'm going to add 1 to it. I guess I should have put n is equal to k plus 1. So I'll replace the n with a k plus 1. So this becomes a k plus 1, this becomes a k plus 1, and k plus 1 minus 1 is just k. I said add 1 to it, but then I wrote k equals n minus 1, so that was, yeah, that's confusing. So I'm changing it so that it has, you're adding 1 to the index, and so in the same time I'm changing the name of the index. All right, so once you get to here, this is your halfway point. What you do is you look at the series on the other side. Well, that's just 0, right? And then you match up the terms with a series on the other side. So imagine this being 0 plus 0 times x plus 0 times x squared plus 0 times x cubed, etc. And then you match it up with x to the 0, which is a constant, and then x to the first power, which is also a constant, etc. So that's all equal to 0. So at this point, you shift over to do this problem where you need to figure out what happens when your k plus 1 times c sub k plus 1 plus c sub k is equal to 0. So the way you're going to do that is solve for the larger c sub k. So c sub k plus 1 is larger, so I'm going to solve for that. Well, you could do it in pieces, but you can write c sub k plus 1 is equal to negative c sub k divided by k plus 1. Right? So how is this series actually going to look like? When k is equal to 0, c sub 1 is equal to negative c sub 0 k plus 1. Wait. 0 plus 1. When k is equal to 1, I get c sub 2 is equal to c sub 1, negative c sub 1 divided by 2. What's this equal to? C sub 0 or c sub 1 is equal to negative c sub 0. So this is negative c sub 0 over 2, right? So that's positive c sub 0. Let's put 1/2 here. K is equal to 2. C sub 3 is equal to negative c sub 2 divided by 3? 2. 3. Right? So this negative 1/2 c sub 0 over 3, right? So this is negative 1 over 6. Why don't I write it like 2 times 3 for now? Once you find a pattern. Or when they tell you how far you should go. So k sub 3, remember this is the second page now. Well, this is a short problem. You guys are going to be doing the second order stuff. This is c sub 4 equals negative c sub 3 divided by 4. So that's negative 1/4 times negative 2 times 3 c sub 0. So negative negative is a positive. 1 over 2 times 3 times 4 c sub 0. You see a pattern? So kn c sub n plus 1, well, it's equal to this. But if you do the pattern, it looks like it's going negative, positive, negative, positive. So it looks like it's an alternating series. Except when is it negative? It's negative on the even problems, right? On the even Ks. It's negative on the even Ks. So when K is even, this is negative. So this should be K plus 1, or N. I'm sorry, it changed to N. N plus 1 divided by, and then I want to go 2, 3, 4. So what should this be? N plus 1 factorial? Right? So my series then is going to look like N, K starts from 0 to infinity of negative 1 to the K. I should have stayed with K. I went back to K. I know, huh?
Is C naught times C naught?
C sub 0, yeah. Yeah. All right. Well, somehow we're over. So somehow this will end up being e to the negative x. What I'm gonna do is I'm gonna make a video this weekend, and I'm gonna have you look at it. Uh, and then so tomorrow, so on Tuesday when we come back, I'm not going to lecture on 6.2 because it would have been on the video already. And so we're just gonna do a quick worksheet, and then we're gonna do a quiz on 6.2. All right, on Tuesday. Okay, so it's dependent on you watching a video on the lecture on 6.2. You can email me maybe. What? No.